All right, new topic. In this section, we're going to be talking about limits and the idea of continuity. And this is really the first time we kind of get into a topic that feels more like calculus to me than pre-calculus. I mean, in one sense, all calculus is the study of sort of what happens mathematically when things get infinitely small or infinitely large. Sure, I guess that works. And our first little taste of these kind of infinite ideas comes when we discuss limits. So it'll feel a little bit weird at first, but fortunately, even if it's strange, it's not super hard. I mean, the idea of a limit, as I say here, is really pretty easy. All that's going on is we have a function. Maybe we'll call that function f of x. And that function can be given to you in terms of its graph, like we have right here, or in terms of its equation, as we see down here. And really, all we're trying to figure out is what height, what output of this function does the graph get really, really, really close to when the x-coordinate gets really, really close to 5. So if you look at our graph right here, when x equals 5, the input to the function is 5. It looks like the output is 8. Because this point 5, 8 is on the graph, we can verify that by taking the algebraic equation of the function and plugging 5 into it. And let's see, if we put 5 in, we got 5 squared minus 3 times 5 minus 2. We got 25 minus 15, which is 10, minus 2 more. Sure enough, we get 8. When you put 5 into this machine, 8 comes out. However, that is not what we want to do to figure out the limit. For the limit, what we want to think about is x values really, really, really close to 5. So not exactly 5 right here, but really, really close to 5. So I don't know, in your mind, maybe you're thinking like 4.9 or something like that, or 5.1 or 5.01 or something like that. It's hard to draw at this scale, but these blue dots are meant to be really, really close to this red dot in terms of their x values. And what we want to do is consider the y values of these blue dots. When the blue dot has an x value slightly less than 5, it looks like the height of the blue dot is some value slightly less than 8. And when the blue dot, which I'm going to change to green to try to make this easier to see, has an x value slightly greater than 5, the y value of that green dot is some height slightly greater than 8. So when the x gets really close to 5, the y gets really, really close to 8. So to answer this question, what height does the graph approach as the x-coordinate approaches 5? We'd say that the height approaches 8. Using more fancy calculus jargon, we would say the limit of this function f of x as x approaches 5 is 8. The way to think about it is when the x value gets close to 5, the y coordinate, the output, the f of x, gets really, really close to 8. This is the way you would say that statement. The way you would write it would be something like this. LIM stands for limit, and the little x in the arrow 5 below the limit reads the limit as x approaches 5 of this function f of x equals 8. And if you want, instead of writing f of x, you could write out what the function actually is, x squared minus 3x minus 2. You could say the limit as x approaches 5, same notation over on the left here, of x squared minus 3x minus 2 equals 8. These are two different ways that we will write this statement, this idea that the y-coordinate's getting close to 8 when the x-coordinate gets close to 5. Not that bad, right? If you're like most students, you're like, all right, I don't really like this idea of gets really close to. Like, wouldn't it be a lot easier to just figure out that this point 5, 8 is on the graph, and therefore the limit as x gets close to 5 is going to be really close to 8? Why not just put 5 into this equation? Let me answer that question with another question. Suppose we had a different function. Maybe it's g of x, and this is the equation of g of x. A little bit uglier, but fine. It's an equation that tells us the output for any input x. What height does the graph of this function g of x approach as the x-coordinate approaches 5? In other words, evaluate the limit as x approaches 5 of this function g of x. If I didn't make such a big deal out of it, you might just try to evaluate g of 5. You might think, and it would make a lot of sense if you thought this, I'll figure out the y-coordinate when x is exactly 5, and that will tell me what the y-coordinate gets really, really close to when the x-coordinate gets really, really close to 5. But look what happens when we try to do that. Plug in 5 here. We would get 5 cubed minus 8 times 5 squared plus 13 times 5 plus 10. And we would have to divide that by 5 minus 5. And what happens here? 5 cubed is 125. 5 squared is 25, and 8 of those 25s is 200. So I got 125, I'll write this, minus 200, plus 13 times 5 is 65, plus 10 more. So I got 75 over here and another 125 over here. I got positive 200 minus 200. Looks like the numerator of this fraction is just 0. And the denominator, 5 minus 5, that's also 0. So what I get when I try to plug 5 into this machine is 0 divided by 0. What in the world does that mean? Well, the problem is it doesn't really mean anything. This is undefined. Can't divide by 0 in math. This doesn't give you an answer. You're like, okay, so you gave me some really weird question where the limit as x approaches 5 of g of x is undefined? No, this is perfectly defined. Because remember, what this is asking is what does the graph's height get really close to when the x-coordinate gets really close to 5? We don't care about the point 5 itself. At the point 5 itself, this function is undefined. But if I look at points close to 5, if I look at like 4.9, for example, I can figure out the output with the help of a calculator by taking 4.9 and cubing it, and then subtracting 8 times 4.9 squared, and then adding 13 times 4.9, and then adding 10, and dividing that whole mess by 4.9 minus 5. G of 4.9, as I'm calculating here with the help of some technology, is 7.31. And you might be like, right, but 4.9, is that really that close to 5? I mean, it's kind of close, but it's not super close. Okay, let's look at 4.99. If I change all the 4.9s into 4.99, my calculator tells me that the output is 7.93, roughly. And in case that's still not close enough to 5 for you, I'm going to make this 4.999. And now my calculator is telling me that the output is about 7.99. What height does this function appear to be approaching when the x-coordinate approaches 5? Well, when this x right here gets really, really close to 5, it looks like this is getting really, really close to 8, even though at 5 itself, the function is undefined. If this analysis doesn't convince you that the function is getting really, really close to 8 when the x-coordinate gets really close to 5, instead of looking at x values slightly less than 5, we could look at x values slightly greater than 5. We could evaluate g of 5.1 by taking our calculator here and changing all the 4.999s into 5.1s. When we put 5.1 into this machine, we see that the output, g of 5.1, is 8.71. A little bit more than 8. And that's not that close to 8, right, because this isn't that close to 5. We could look at g of 5.01 and g of 5.001 to better understand what this height is approaching as x approaches 5. When we put 5.01 in, it looks like the output is about 8.07. And when we put in 5.001, the output is about 8.01 if I round to 2 decimal places. And maybe these table of values is sufficient to convince you that the limit as x approaches 5 of this strange function g of x is actually equal to 8. It's not undefined, even though g of 5 itself is undefined. Maybe I can capture that idea with this important observation here. And if you're like most students, you're like, all right, I mean, you kind of lost me with all these calculations. I don't quite understand what's going on. Is there any way you could give me like a graph? I understood this a lot more when we're talking about the x value getting close to 5 and the y value getting close to 8 when the 0.58 was on the graph. What does the graph of g of x look like? It might surprise you a little bit. The graph of g of x looks almost identical to the graph of f of x that we had up here. The only difference is g of x has this little open circle right here, this hole. It's what's called a removable discontinuity. More on that later. And because it has this open circle here, when you try to plug 5 into this machine, there is no defined output because the open circle is not part of the graph. However, when we plug in values that are slightly less than 5, for the sake of the picture, I'll denote slightly less than 5 as right about here, although really you could argue that's not that close to 5. What comes out are y-coordinates that are slightly less than 8. And when we plug in values that are slightly greater than 5, which I'll denote with a point right here in green, what comes out are values that are slightly greater than 8. And even if it leaves you feeling a little bit uncomfortable being able to sort of guess that the limit as x approaches 5 of this function g of x equals 8 based upon these values, at this point in the class, that's kind of the best we can do to evaluate this limit because we can't just go plugging in 5 because g of 5 is undefined. And you're like, I guess. I mean, this looks like a more normal function, and this looks like some really weird example that you, the teacher, made up just to prove a point. Like, how often is this really the case? It turns out that this is the case in calculus. You don't understand why yet, I totally get that, but this graph is going to be the normal graph, not some weird graph. This, surprisingly, would be some weird graph for the purposes of calculus. For our purposes in this class, the problems we're going to run into are going to look like this. So the limits we'll need to evaluate will be limits like this, where the value of the function is undefined at that point. This observation is so important that even if a function is undefined at a point, we can still talk about its limit by using the ideas that we've captured in this video. I got a lot more to say about limits, but for the sake of keeping these relatively digestible, I'm going to quit this video here.